Let's talk about the weighted standard deviation. Or before we talk about how to calculate the weighted mean, let's remind ourselves what we're trying to do here. So if we have a distribution and we've plotted it on a number line and it has a nice bell curve, we have a mean right here. What we're trying to do with the standard deviation is figure out how far from the mean a typical value is found, right? And if you remember when we talked about it, we go about -3 standard deviations below and about +3 standard deviations above. And inside this first group, 1 standard deviation above or below the mean, we have about 86% of our values. We have about 95% within 2 standard deviations. And within 3 standard deviations, we essentially have 100%. It's 99.7, but it's essentially 100%. Okay, so what we're really getting at is how dispersed our data are. And when we talked about weighted means before, we talked about a hamburger stand where we were trying to weight the price by the frequency with which someone ate at our restaurant. In this case, just to keep it a little bit simpler, I'm going to make these values a little bit easier. Okay, so we have the data set 1, 2, and 6, and we have the weights 2, 2, and 4. And just like we did with the weighted mean, we're going to weight these by multiplication. So this 1 becomes a 2 because we have 1 times 2. This 2 becomes a 4 because of the 2 times 2, and this 6 becomes a 24. So this latter value, the 6 here, I mean, it was already the most significant player, but when we weight it twice as much as anybody else, that's going to become the big factor in our calculation here. So the usual standard deviation, if you remember right, the equation was each observation minus their own mean, squared, summed, and divided by n minus 1. Okay. What we're going to do now to change this a little bit is we're going to use the weighted mean down here. And I didn't really leave myself much room here, did I? But we're going to multiply this by the weights before we sum it up and take the square root. And then here in the denominator, we're going to get rid of the n and replace that with the sum of the weights again. So remember, our sum of weights has to appear in the numerator and in the denominator so that they cancel each other out in the calculation and we get back to our original units in the same way that we have to take the square root before we do after we square it. So it looks like this. Here we have our data, 1, 2, and 6. The mean of these data, the weighted mean, is 3.75. So I'm going to subtract 3.75 from each one of these observations, which gives me, in this case, -2.75, -1.75, and 2.25. And then we're going to square these data, which gives us 7.56, 3.06, and 5.06. Okay, so that's gotten us up to here. We've done the math. We've subtracted it from the weighted mean. We've squared it. And now we need to multiply by the weights. So this gets multiplied by, this gets multiplied by 2. This gets multiplied by 2. And this gets multiplied by 4. Okay, and when we do that, the answers that we get, I've kind of run out of room here, so I'll put them on the bottom, but we end up with 15.125, 6.125, and 20.250. When we add that up, it is 41.5. Okay, so back here in our equation, if we have the square root of now 41.5 is in our numerator. Okay. The denominator is just the sum of our weights, which sums up to 8. Minus 1 is 7. So we have the square root of 41.5 divided by 7, and that answer is equal to 2.435. Okay. Now let me just illustrate one concept here. I'm going to get rid of all of this room. I need a little bit more space. But this is exactly the same thing as if we had, if instead of multiplying the 1 by the 2 right here, if we just wrote out, I keep doing that. If we just had 2 1s, 2 2s, and 4 6s, right? If this was our data set, and I just got that data set by, right, here I have 2 1s, 2 2s, and 4 6s. And then I just calculated the normal standard deviation of these values, I would get this answer. Okay, so either way will get you the right answer. Of course, we can weight by things that aren't whole integers, and then that makes it difficult to use this other method. But that's really all we're doing here. So it's really not that complicated. All right, let's look at calculating the weighted standard deviation in R. Unfortunately, there is no weighted standard deviation function, so we're going to have to create our own. But let's open up our data. This is x. We had equal to 1, 2, and 6. That was our very simple data set from our example. And our weights were equal to 2, 2, and 4. Okay. So let's create a function that will calculate a weighted standard deviation. So I'm going to call it weighted standard deviation. It is a function that has as its inputs x and f. Actually, to make this a little bit less confusing, I'm going to call this data and this weights. But in here, we'll just refer to them as x and f, and it looks like this. First off, we need to calculate the weighted mean, which, if you remember, is just the sum of x times f divided by the sum of f. And then we're going to calculate the deviations there. So this would be x minus m. This gets squared, then multiplied by f, and then summed up. Okay, there's our numerator. And our denominator then is the sum of f minus 1. And then we take the square root of the whole thing. Okay. Once we have created a function that calculates the weighted standard deviation, we should just be able to input data as x and weights as f, and it should work. So I will highlight that all. I'm on a Mac, so I will hold down Command and hit Return. If you're on a Windows machine, hold down Control and hit R. And here we go. Here's our data and our weights. Here's our function that calculates the weighted standard deviation. And here's the answer, 2.434866. The biggest issue that I have when I create this is almost every time I do it, I forget that I have to calculate the weighted mean to use here instead of just the standard mean. But once you do that, calculating the weighted standard deviation is very, very easy.